Good afternoon, everyone. Thanks for coming. Thanks also for people joining on Zoom. I think we have actually a bigger class on Zoom than physically. Thanks for joining. So the goal is to give a short introduction to reinforcement learning. It's a course I give in South Africa over a month also. So the goal for today is to introduce the ideas of reinforcement learning, what we'll be covering in terms of theory. So I'll start with some easy examples to set the tone and the context. And then today we'll start also the material with Markov processes. So just a recap of what Markov processes is. The main model to study reinforcement learning is called the Markov decision process. So we have to learn a bit what Markov processes are. Then there'll be a second chapter on Markov reward processes, and then we'll get actually in the second week already in Markov decision processes, and then we'll use those actually to do the whole theory of reinforcement learning. And then I'll give more information. There'll be courseworks as we go along, and then there's a final coursework on a robot navigating a certain world. Okay. As Abhishek said, if you have any questions in the audience here, please stop me. So this is a course, so it's supposed to be interactive. And also for the people on Zoom, you can unmute yourself and then ask a question. You can just call my name, and then we'll listen to the question, and then I'll try to answer that. Okay, so reinforcement learning is about learning a task with interactions. So we're very familiar actually with the idea because this is how we learn. This is how we learn to talk, to walk. And so the idea is that you have a kind of a world or a system that you're interacting with, and then there's an agent or a controller or a person or a robot or machine or something. And the goal is to learn a certain task by acting in the world and receiving some kind of feedback on this via observation, but also via reward. So the idea is that you learn from interaction. So I'll come back to this example a lot, but imagine a baby trying to walk. So the baby will try just to move his limbs first, the legs, the arms, and then we'll just try some actions, trial and error, and then nothing is really happening. But this is what we call the exploration phase. So you actually get your relationship with the world, and then you make some actions, you see the observation, and then you just continue doing action based on the observation or the results of these actions in the world. And the point of learning is to reinforce the good actions. So you want to reinforce the good actions that will lead you to achieve the task. So in this case, the baby will learn gradually to do some particular actions in order to walk. And those actions will be reinforced in different ways. Physically, because the baby is going to fall down in different ways, but also from the parents. So the parents will reinforce certain actions and will be pleased to see the baby doing some actions, and then will be reinforcing those actions. So it's a goal-directed learning, and the goal really is driven by a notion of reward that will be central to learning. So the way that the reinforcement is done is by assigning reward to certain actions with respect to certain state also of the world. And these rewards can be very implicit. So in the case of a baby, again, it could be the parents actually giving rewards, sounding happy, patting the baby, but also physically the baby is injuring herself as the wrong actions are being done. So there's lots of reward, and then we'll talk a lot about the reward. The reward is not something that's always given. You have to think a lot about designing the right reward to actually achieve the task. And the goal is to find the optimal way to act, and this will be the notion of optimal policy. So we have a few notions here that I'll talk about a lot, and I'll be using those words. So exploration, the idea of reinforcing is exploitation. And so in reinforcement learning, we have this tension, this balance between exploration and exploitation. You cannot just exploit, you need to learn first a bit, so you need to explore, but once you've explored enough, you can start exploiting the actions. And this is driven by the reward, and the goal is to find an optimal way of achieving the task, and then technically this is called an optimal policy. It's like an optimal control. What's important in learning is that the reward is not just given for the action you're doing right now. So this is not just immediate reward. Reward should be also given for something that's going to be achieved in the future. And so we'll get to the notion of return. And this is really important. If you try to only learn with immediate reward, it's not going to work, actually. It's too short-sighted in terms of learning. And so you have to actually propagate the kind of the consequences of your action, and you have to see those consequences far in the future in order to learn from your action. And so we'll see this also. And what should be clear also is that the actions will depend on the situations. And so this is what we call associativity. And then the whole model will be based on Markov processes and random variables and Markov chains and so on, because we want to build in the idea that everything has some uncertainty or noise, right? So the way that your actions are actually implemented in the world might be noisy, or it might not be deterministic. So you have to model the action as a random variable. The world itself is noisy and uncertain, so you have to model the world, the state of the world, also as a random variable. The observation is a random variable as a result. So the whole thing is actually a kind of feedback loop that has to be studied using probability theory, and then we'll do this. You could build a theory of learning actually just based on dynamical system and deterministic systems if you wanted. But if you do a theory based on Markov processes, actually, it includes the deterministic world as well. So you might as well just start with the full probabilistic model of what learning is. And if you want to apply it to systems that are fully deterministic, then you can apply the theory as a particular case of the theory. Okay? Okay, so the fact that you can actually learn via reward and only via reward, right? The point of reinforcement learning is that you don't have a teacher on the side. So the person, the agent, is not being told what to do. The whole point is that the agent should learn actually what should be done just based on interaction. So this is like an agent-centric kind of learning. And then I'll contrast this later on with different types of learning that you can imagine in machine learning, like supervised learning and unsupervised learning. So this is all driven by reward, and the fact that you can achieve learning via reward is what we call the reward hypothesis. And the practical version of this is that all goals can be described by maximizing a reward. Okay, so the reward communicates what needs to be achieved, as opposed to actually saying explicitly in terms of rule what needs to be achieved. So this is very different from the way that we program normally. If you program a computer, you would want actually to specify all the recipes, but now the learning will be done gradually with the interaction of the environment. And then another example to imagine is self-driving cars, right? You could program maybe a self-driving cars and putting all the programs for the car to do everything in every situation. This will be difficult. The paradigm of machine learning or reinforcement learning that's being applied to self-driving cars is that you should actually let the cars learn how to drive and then get an implicit representation of these rules as opposed to actually making those rules explicit. And this is actually much more powerful. And if you think about it, this is really how we learn. Even how we learn theory, how we learn to walk, talk, and everything, the learning is done gradually without explicit teachers. Okay. Then you could say, well, what about school? I mean, you have a teacher telling you what to do, but the teacher really, if you think about it, is only a form of reward. Right? The teacher is reinforcing the good actions and going in the right direction. He's not always telling you what to do exactly. Of course, it has that form too, but you can perceive education as a whole also in terms of reward. So that's the practical version. There's a strong version actually that's being explained in this paper of David Silver. David Silver, I'll mention his name later on too, is a researcher at DeepMind. He studied at UCL before. A strong version of this is that any kind of intelligence is actually driven by reward, right? So maximizing reward is enough to drive behavior that exhibits most, if not all, abilities studied in AI or natural intelligence. So this is a bit controversial. This touches more about philosophy. We can discuss this if you want after the class. We'll go into the practical version of learning with reward. So we'll build a theory that's based on the notion of reward, and then we'll implement this in various situations where we have to learn a given task. So this is the model more mathematically, right? So it's the same kind of loop between a system, an agent, and doing actions, but now I'm going to put variables that will denote what we'll be doing, and also these variables will have an index denoting time. So it all starts with, you have a system, and then as an agent, you can observe a state. So at time t, this is the state of the system. The system can be different things. It can be a particular system, it can be the state of the world, it could be the state of the universe. We'll come to define this, right? It depends on the application. So the agent actually sees that state, and the agent will be taking an action based on that state. And the action will be denoted by A. So this is the action done or acted or chosen at time t. So this will be the random variable A of t. And then out of this action and the state of the system, there'll be a given reward given to the agent for having chosen this action, right? So what we have is that there's an initial state of the world. The agent will take action at that time. So this is the initial action. A reward will be given actually for the state and the action. So this is a reward that depends both on the state and the action that's been chosen. And at that point, then the state of the system will change to a new state, S1. The agent will take a new action, a new reward will be given, and then so on. So this is a kind of unfolded loop. This is the trajectory of the full system, the agent, and the world. We're going to take discrete time just to make things simpler, but you can imagine this actually also running in continuous time. But for the purpose of this course, everything will be in discrete time. So you just have time snapshot. There's a state. I'm taking an action. I receive a reward. Everything changes to a new state. I'm going to take a new action. I receive a new reward, and then so on. And this will be the trajectory of the combined system, agent, and system.
Because you have probability of ST plus 1, RT plus 1, you mean that the action does not determine ST plus 1.
It will. So this is what I'm gonna say. So this is the trajectory. Now we have to define the dynamics of the system, and then we have to find also what we call the policy or the control. How do we choose given actions depending on the state? So at the time t. So there are two basic objects that I'm going to need to specify actually in the model. One is the dynamics. So you see, this will give me the probability that the system changes state at time t plus 1, that I receive the reward actually, given that I started the system at that state and then I took this action. Okay, so the dynamics will be encoded as a Markov process. And I'll mention a bit more about this actually when I get to the chapter, why we choose this model. But this is a simple model that has probabilities built in. I'm dealing with random variables, and it's the simplest model that has a dynamic. So again, given that this is the world state at time t, I'm giving this action, then it's going to trigger a transition to a new state for which I'm going to get a reward r plus 1. Okay, so the new state is triggered implicitly by the choice of the action, but also maybe by the dynamics of the world itself. Okay, and this is all encoded into this. This doesn't say actually how the agent chooses the action. This is another now distribution that we're going to have to specify, which is the policy. So this is the conditional distribution of choosing a certain action given that I see a certain state. Okay, so given that I have this observation, this is the probability that I take this action. Now, this doesn't have to be a probability. Most of the time, actually, we'll see that in a given state, I'm going to choose a given action. So the choice of action will be deterministic given the state. But I could choose to randomize my action, and this will be encoded in this probability distribution. Yes?
Do you think those depend on the reward?
No, so the dynamics doesn't depend on the reward. The only thing is that we'll see that the reward will play at the level of the control. I'm going to be choosing certain actions according to the reward that I'm being awarded over time, okay? But the reward is not included here in the conditioning. I see a certain state, I'm going to take a certain action. Out of this, I have an evolution to a new state. I don't have to evolve the agent, right? The agent is only choosing an action, but out of this dynamics, I'm getting a reward, which could also be random, right? So it's included in the distribution. We'll see more of this. I just want to introduce the big ideas, but when we get to chapter 3 on Markov decision processes, then we'll redefine all of this very precisely and explain what it means in terms of building an approximation of really of what control is. Okay. Yes.
Why we considering this? Hello. Why we are only considering the previous state and this action, not the all other like past ones? It may affect or not.
Oh yeah, so this will be the Markov approximation. Of course, I could take an action based on the whole history of state that I've seen and the whole history of actions that I've taken. We're not going to do this. If we did this, it would be a very complicated model. So I'll explain this in chapter 3 when we get there. Actually, it's going to be next week. Chapter is actually going to run very quickly. You'll see this. So the question is, why don't I include more information in the past for the dynamics? And this will be the Markov approximation. Okay, so that's the simplified model. That's the model of the Markov decision process that we'll get to see, that we'll study actually for most of our time. And then we have, again, this division between agent and the world. And in practice, that division is not always clear-cut, right? So we have to think about this. In a sense, in this course, you have to take your physicist brain a bit aside and then try to just use an engineer brain, if you can do this, and to think very precisely about building a given model that's actually useful for the task that you want to learn, and then trying to find the best variables actually that describe these tasks. Okay, so this is not always explicit or obvious, and then we need to think about this. Okay, so reinforcement learning in that sense is it's a particular field of machine learning, but it's different from other types of machine learning that are also part of machine learning. So there's something called supervised learning, which is a very common field in machine learning, lots of applications, where you have a set of training examples, like for instance, you want to classify pictures of cats and dogs, and so you have a data set of pictures with cat pictures with a label cat and dogs pictures with the label dogs. And so you can give this to a neural network, and the neural network can learn to classify those pictures because now you have examples of what to do. And so the rule is actually learned. So there's instructive feedback in the sense of supervision in the training set of examples. So in a sense, you have an external supervisor telling you what to do, and then you just have to learn that rule that the supervisor is telling you what to do. So you extrapolate, you generalize. There's no interaction here between the data set and the learner. You have the data set, you're just learning what the data set is telling you. Reinforcement learning is very different because there's no example of desired behavior in the first place. The problem is only that you're interacting with the world, you have a certain reward signal, but nobody is telling you really what actions you should be taking. Even at the start, nobody is telling you what is the goal of the task. This will come implicitly from the reward signal. Okay, so you can imagine learning chess without being told actually what the rules of chess are. But if you give a reward signal that gradually tells you what the rules are, then you can learn chess actually without being told any specific rules. So there's no example of desired behavior or goal behavior. There's no representative set of examples. So the history actually will be generated as we learn. It's not like we're looking in some book with examples of people who have learned, and then you see what they have learned. You actually do the learning yourself. So you learn from experience, not a training set. So this is very important. And that makes it very different from supervised learning. And so what we have to do is this exploitation. We have to evaluate the consequences of action in terms of reward. So that's the exploration. And then we have also to exploit with time actually the good actions that will lead to the task being achieved. And this is done in a non-line way, in an interactive way, in the same way that kids learn to talk and kids learn to walk. Yes.
I have a question, Hugo.
Yes.
Hi.
This is
How do you know that you are not learning something wrong? I mean,
this is a very good question. So a priori, you don't know. The hope is that if the reward signal is good and well designed, then it should lead to learning the right task. But we'll see actually in simulation, you'll see this in your coursework, that as you run simulation, you'll see that it's not going in the right place. So you have to restart the simulation and then do another simulation. So the convergence to learning the task is actually probabilistic also. Because we have a probabilistic model, the evolution of the learning will also be probabilistic. Our goal is to make sure that we have the right policy and even the right reward signal to make sure that learning converges. But this is a very important question. There's no guarantee of convergence of learning, in the same way that actually kids might take a long time before they talk, or they might take a long time before they walk. Some kids, if left on their own, might not even learn to talk ever. So you have to design the right reward signal to achieve learning.
Thank you. Yes, thanks.
Hugo, a question here from online. So in the previous slide, you said the control actually depends on the action of the control, depends only on the state. And why not? I mean, the picture actually depicts there is a feedback from for the reward as well. So are we missing that, or?
No, we'll see this. The action, of course, takes care of the reward, but the way that you model this will only be on the state and the action. You only want to specify a policy that will maximize the reward. So we'll get to see this. So again, I'm throwing the ideas. It's not all clear now, but we'll get to these concepts like very clearly when we get to the chapter. So the reward will lead actually the learning, and the reward will actually lead the choice of a policy. It's not explicitly as a conditioning in the policy, but we'll see actually that it influences the choices of policy.
So yeah, I'm a little confused about why you're making a distinction between supervised and why can't you see the supervisor as an example of a reward? You know, if the supervisor says this is right, that's a reward, and if supervisor says it's wrong, that's
no. You could actually say something like this. I think the one thing that's missing is the online interactive nature of reinforcement learning that you don't have normally in supervised learning. So supervised learning has a loss, so it has a notion of reward. So you want to maximize actually you want to minimize the loss. So you're choosing your weights in a neural network in order to match a certain function, and that minimizes the loss. So in a sense, the loss is the reward. That's true. In a sense, actually, I could put a diagram, all these paradigms of learning, they have some overlap, so they're not totally distinct. So they share some commonalities, and it's fine. But the one thing that you really don't have in reinforcement learning is a training set of examples, and then what you have is really this online interactive nature of learning, and that makes it different. Okay. We'll get to see this also. There are ways actually that you can frame actually supervised learning as a reinforcement learning way. Yes. Yeah. DeepMind has done some work on this actually and learning good compression of signals using reinforcement learning. And this works. Okay, there's another type of learning that I'm not going to discuss so much, which we call unsupervised learning. This is another field of machine learning where you're trying to do classification without data. You're just trying to find some structure in the data, and then there are different ways you can do this, and it's not necessarily based on a notion of reward, though sometimes unsupervised learning can also involve some kind of reward. Okay, so this is the plan for us. So again, I'm just putting the ideas to give you an idea of where we're going. So it's really learning at large in a reinforcement learning kind of way. And so the plan for the course will be 4 weeks. So we're going to start actually in the first week with Markov processes. So we'll see today Markov processes. Tuesday next week, we'll see Markov reward processes. And the goal is to get on Friday actually to Markov decision processes, and then we'll spend some time on this. And then the main theory of reinforcement learning is what we call dynamic programming, and it's based on a few equations that we call Bellman equations. So we'll see this. And then I want to get as quick as possible to the 4th week on actual algorithms that achieve learning. And the algorithms that we'll see, they're called TD algorithms, temporal difference algorithms. And the main one we'll see is Q-learning. So we'll see SARSA and Q-learning. They're very similar, but the one we'll be using mostly is Q-learning. And this will be applied in 2 coursework. So the first coursework is already out. You'll be able to start on the first coursework actually at the end of the lecture. And it's on application. So we'll be working on over about 3 weeks on all the theory. And then the questions are designed so that when I finish something, you can do more questions in the courseworks, and then I'll lead you into this. And then the final coursework will be something at the end of the course. So I'm not going to oversee this. It's something that you can do for yourself. It has to do with a 2D navigation system that's based on the Python package GIM, which is coming from OpenAI. So this is a kind of learning package for reinforcement learning. That's quite nice because many environments are coded, so you don't have to code maze yourself or games yourself. So you can just implement the kind of learning that you want. We have many students in the course. I don't have time to answer all questions. So we have an assistant, a teaching assistant. So Umesh Kumar has kindly agreed to assist me in doing this. That's his email. I'm putting his email with his permission here. If you have any questions about the coursework or the theory, you can email Umesh. If the questions are too technical for Umesh, then I'll get the question and then I can answer. But for me, I'll be flooded, and so I need some help to run the course. The material is, I put it on GitHub. So this is a subdirectory on my own GitHub. So you have the address here. So for instance, these slides are there now. All the lecture notes for the 4 chapters that we have are there now. The coursework, the first coursework is also there. And eventually I'll put the solutions also for the coursework. There's also an information sheet about the course on the GitHub that lists kind of the synopsis of the course, but also some references. The main reference in reinforcement learning is a textbook by Sutton and Bartow called Reinforcement Learning, and then you have that reference there. There's also a HTTP link for that book because you can find that book for free. So I'm not putting the book here, but it's on the information sheet on the GitHub. The courseworks are based on Python. So if I'll give the solutions to the coursework, everything will be coded in Python. In fact, I'll give you just a notebook, a Jupyter notebook with the solutions I'll explain. The solutions in Python, they don't involve a lot of programming. The ideas are very simple. So I think to follow the course, you have to have a good basis or some experience in programming in Python. You have to have some background in probability theory, so knowing about random variable distribution, continuous distributions, discrete distribution, expectation, what's the mean, what's the variance, things like this. It will help if you've seen Markov chains already, but I don't think it's an ultimate prerequisite because I'll see Markov chains today. And if you need more material for Markov chains, then I have actually, I teach Markov chains also in South Africa. So if you type my name and Markov chains or Markov processes, you'll get to the website of that course. And then there's some material also. So you can follow some material there if you want to learn about Markov chains or just recap your knowledge about Markov chains. Okay, now before I go to the theory, everything will be on the blackboard. So I'm just going to finish with some more examples of learning just to fix the ideas again, and then the kind of concepts that I'll be discussing. So here is an example of a maze. The task is to find the goal, so to get out of the maze by starting in that direction. Okay, so imagine that you're actually walking in this maze, so you don't know where the exit is, so you start walking, and then you have to decide here where you're going. Are you going left or right? And then, so you have a bunch of actions, right? So the state of the system in this case is your actual state in the maze, where you are in the maze. The actions can be north, south, east, west. Okay, but these actions, they're not always possible depending on the location. So in a sense, if you're here, you can only go south or west. You cannot go north or east. So the actions depend a lot on the state in which you are. And so this will determine the kind of policy that you can choose. Okay, so you imagine doing this, and then you walk for a bit of time, but at some point you're going to reinforce the idea that you're not going in the right direction. For instance, you get stuck here, so you have to backtrack and then try another action. So here you'll actually, if you walk inside the maze, you will do reinforcement learning to reach a certain goal, and as you exit, it's going to be easier now to start and actually do it again. You might not do it again in the first place again. You might just don't remember exactly where you have to go, but you're going to have some knowledge that starting from here, don't go down, go up, and then it's going to be easier to exit. Okay, so here the reward, in a sense, you can view the reward as -1, so a kind of penalized reward for every step that you take. So as an agent, you want to maximize that reward, right? So you want to have the least negative reward in this case, because you want to achieve going out of the maze in the least number of steps. So one way to achieve this will be to have -1 reward per step. Or, so this is one possible reward that you can imagine. Another reward could be that you give a reward just when you exit. Okay, so then it's clear that your action has to depend on future reward. Because if they don't, you will never actually exit, right? Your goal will be to exit, so your goal is to actually get that final reward. If you have no idea that there's a final reward, there's no learning that can be achieved. If you have this, there's also learning that can be achieved, but you have to take account also all the steps that will go into the future. So also the learning here has to depend on the future. So at the end of the day, actually, if I do the learning task and I solve the learning task, then I'll get a map like this that tells me actually what I should be doing. So this actually is the solution of the control task. If I start here, it tells me go forward. If I get here, it tells me go up. And then it gives me all the directions. So if I had those arrows painting on the floor, I would actually get out in the least number of steps. Okay. You also have the map for the other states, because for instance, if you don't follow these arrows and just to decide to go down and then you're here, then actually this arrow is telling you, no, you have to go here, go here, go here, go here. So you can actually tell what the solution of the action is for all the states of the universe, even those states that you're not going to see at the end as you achieve the task, okay? So again, this is the solution. You don't have this to begin with. This is what you want to reach. And this is also related to what we call the value function that will tell you actually what's the reward. So if you start, here you're going to see the number -16 because it tells you that the number of reward to get to the exit is -16. Now, as you go here, it tells you -15, and then here you see, oh, if you go down now, your reward, your return, your future reward will be -16, whereas if you go up, the future reward will be -14. So where do you go? You go to -14. Now, when you get to -14, this one tells you that, oh, you have now this -13, so you should go forward. If you're here, then if you go down, you will actually increase the future reward that you're going to have, so you better actually go there. So if I can actually assign to each state what the future reward from that state will be, I have also a solution to the problem. Okay, so giving a map like this or giving all these future rewards for each of the states is also a solution. So we'll see this a lot. This is the policy. This is what we call the value function. And to solve a reinforcement learning task, I need to define this notion of value function. And my goal as an agent is always to go in the direction of a maximum value function. I want to go into states that will maximize my future reward. This is the goal of the agent, and this will be very important. So if you think of learning as a baby, the baby actually, what the baby learns is that the baby sees the reward or feels the reward, but in some implicit way also, the baby is taking actions that will maximize future rewards, right? So it can do a mechanical action, not just for the benefit of this action at this given time, but because the baby knows or has learned that the parents will be happy later on when he's able to finally stand up. Okay, so the idea of future reward, again, is very important. Okay, here's another example, which is an example that's very important for us because it's going to be the example that I use mostly for the coursework and for illustrating many of the theory that I will do on the book. So this is a simple example coming from the Stanford reinforcement learning course. They call this the Mars rover example. So it's basically just a linear chain of states. So this is like the simplest model we can imagine of being in a state and moving. So here we have 7 states. This is arbitrary. It could be 3 states or 5 states, doesn't matter. And then in the reinforcement learning course at Stanford, they number from 1 to 7, but I'm going to number them from 0 to 6 because I use Python. So I have a linear change. So I have 7 states, 0, 1, 2, 3, 4, 5, 6, and I can move left or I can move right. And here it's just an example that's been invented like this. There are 2 rewards. So there's a reward if I exit from 1 to 2, and I'm going to have a reward of 1. So if I do an action to stay in the state S1, I'm going to get a reward 1, but I also have a reward 1 for exiting S1. That's good. I also have a reward 10 if I reach 7 and I exit 7. So this, I'm going to get a reward 10. And if I stay in the state 7, I also accumulate a reward 10 for every time I decide to stay in that state. So there's a small reward on this side. There's a big reward on this side, okay? And the goal is to maximize the expected reward in the future. So with moving only left or right. So you imagine that the robot actually will have a tendency with time to go on the right. Okay, right, yes, right. But initially the robot doesn't know, it doesn't know the reward structure, so it's making movement, but it's not receiving any rewards for the movement done in the center. It's only going to accumulate rewards by reaching one state and the other state. Now you can imagine the case where the robot goes here and then finds the reward 1. It's just like, oh, this is great, I'm going to stay here, I get a reward. But it's not maximizing the potential return that it can get in the future, right? So it still needs to move in order to reach the number 10, and this should be really the ultimate reward that can be accumulated for this task. So we're going to use this example exactly to see the dynamics of this, the exploration and the fact that you can get stuck in the wrong task and then you're not maximizing fully what the future reward is. And also to illustrate the fact that the future reward is very important and not just the one-step reward. There's no reward in the middle, so as you move left and right, it doesn't make any difference. So you have to have a sense that there's a reward coming in the future in order to actually choose the right action in the middle. And this will be done. So here, what's the state? So what we have to think is that every time we're defining a model like this, we have to define this. Yes?
You said there's also a reward for exiting on the left, or is or do you
No,
just
so this
loop
is
on
a
the side?
closed universe. So I can, if I reach here, I can only go back or stay in the state, or I can stay in S1.
Okay.
I cannot leave this
Okay,
world.
good. So there's a loop also on the right-hand side, I
Yeah,
guess.
yeah.
Left-hand
So
side, yeah.
I have two action. I can move here on the left, but if I'm already at 0, moving on the left means that I stay at 0.
thank
Or I
you.
can move on the right. If I choose this action and I'm in the state 6, it means that I'm just staying in the state 6. So I get stuck in the two extremal states. Okay, so this is really important. I want to emphasize this again. I have a given task. I need to define what's the state, what are the possible actions, and what the rewards. These are always the three ingredients that I need. So the state is the location of the robot, the rover. The action is I move left or right, with, again, the proviso that I'm not exiting the system. And the rewards is that I have a +1 from exiting the state 0 here, or a +10 for exiting the state 6. Exiting meaning I go out or I stay in it, okay? This is a made-up example again. We're just going to use these rules and these rewards. Yeah.
So why is this model called linear model?
It's linear model because it's just a linear world, right? It's a one-dimensional world. So if I think about the maze here, this is a two-dimensional world. This is a one-dimensional world. So it's a linear model. It's not linear in the sense of linear algebra. Yeah.
Usually in the other forms of learning, we are sort of familiar with this training and test phase, right? So
Yes.
here that's kind of not happening. Is that right?
It's happening and not happening. You could imagine having a robot learning a certain task and deploying the robot in a different environment. So in this one, there will be a kind of learning phase and a deploying phase, which would correspond to a testing and then an application phase. But we're not going to see this. This is a topic on its own, and it's very important. This is also related to the notion of generalization. You know, if you train a self-driving car to a certain environment, you want to make sure that the car is driving in all, environments like good environments. And so you could imagine this notion of training and testing, but we're not going to see this in the course.
Okay, so even in the maze example on the previous slide, if I'm exploring and I find myself at the reward, then I kind of, in my mental model, then I'm not ever moving away from this reward.
No, but you
Or
can.
am I resetting back to the? Okay.
Yes.
All right.
Because it could be that you haven't fully learned the full solution, and so you have to start. Okay, so this is an example that we'll see again. I'm just putting it out to explaining something, but I'll explain the model again, and then you'll see it again in the coursework. It's explained in the coursework, so you're going to get tired of seeing the model. But it's a good one for teaching, okay? So that's why we use it. Another example, which is one of the last questions in the first coursework, is an exercise that comes from this textbook from Sutton and Bartow. It's example 3.6. This is now a two-dimensional world, so you can move on that grid, and there are different rules. So you can move north, south, east, west again, but you cannot go out of the world. So if you're trying to go like this, you get out of the world, you get a reward -1. If you reach A, you're actually being teleported to A prime with a reward +10. If you reach B, you'll be teleported to B prime with a reward of +5. Okay, so the state of the system now is your location on the grid. The action is north, south, east, west in terms of movement. And the reward is you get penalized for trying to leave the grid. And then you have a reward +10 for reaching A, a reward +5 for reaching B. Okay, so if you look at this, it's clear that you should move to A, right? So the optimal policy should be pushing you to A, and here I'm showing the optimal policy. And again, the optimal policy is a map of the action that you have to take at a given state of the system. So it's an action that you have to take for every location in the grid. So here, this is the solution. So if I sit here, it tells me go up. Then I go here. Then it tells me go up. Then I go here. Then I go here. Here, it doesn't matter what I do. I could choose any of the actions because I'll be teleported back to here. If I'm anywhere, then the solution will tell me what to do. And then you have some kind of degeneracy. So here, for instance, I have two possible actions because it happens often actually that doing one action or the other is not changing your overall gain and reward in the future. So you have some kind of degeneracy in the actions you can take. And this is possible. And then you see this. So this is what I want to find. This is the optimal policy that we want to find. We want to find the best actions that will lead to a future reward. And the best action will be a map of what action has to be taken for a given state. An equivalent way of looking at the solution, again, is the value of each state. So if I'm here, this is the value. So it says that if you sit here, actually, your expected reward in the future will be 17.8. And then you look around, and then you see that there's a bigger reward here. So you have to move here as an agent. This will give you now a better reward in the future. So knowing this actually tells you which action you have to take. So in the theory, we'll try to calculate this, and this actually will give us the optimal policy. Okay, so the game will always be the same. We will define a model as a Markov decision process. There'll be a bunch of states, a bunch of action, and our goal is to find the value in the future of each state. Based on this value, I have the solution of the optimal policy I need to find. Okay, so the maze example, you have to keep this one in mind. Yes?
So in this example, each step is not penalized, right? You're not penalizing.
You have no reward for taking a step. There are only 3 possible rewards, right? And these are just made up rewards. I could choose the rewards in a different way. It will define a different task, right? So here for this world, I choose my states, I choose my actions, and I choose the reward structure that I have for this problem. So no reward for moving.
Why does it matter how you get to A, in what path you get to A?
Because, so here actually behind this, we'll see there's a kind of parameter that tells me the strength of the reward that I want to get. So implicitly, there's also the number of steps that plays here. I want to get that reward in the least number of steps. Yes. This will come with a parameter gamma that comes in the theory that actually is weighting the importance of the future reward.
A quick question from online. This is anyways. So you mentioned about online and interaction. My interpretation is the whole of reward landscape is partially unknown. Now the previous 2 examples you showed, it looks like as if the whole reward landscape is known. So where is the online and interaction part in the previous 2 examples? Also, why the second example is linear model?
So the reward is always explicit. The thing is that the agent initially doesn't know what reward is associated with which action. So there needs to be an exploration phase. So again, think about learning anything. I will do some actions and receive rewards for those actions, but it doesn't tell me right away what the good actions need to be done, because I need to actually accumulate those rewards in the future to see which action will do the best in the future. So I need to explore. So the reward structure is always explicit. It's given in the model. This will always be given: the states, the action, the reward structure. But giving these 3, I still don't have the solution of what needs to be done in time to achieve the maximum future reward. Okay, and then I think I'll leave it here for now because I think it will become clear as we go into theory. The way all of this is actually related, the state, the actions, and the reward, I think will become much clearer actually when we get to chapter 3. So I'm just gonna keep the question here suspended.
And what about the second example? Why is it linear model?
No, it's linear just because it's a one-dimensional world. So nothing to do with linear algebra.
Okay.
It's a line. Okay.
Sorry, say one second. You say -1 if leaving grid, but isn't this also a closed universe?
Yeah, it's closed universe, but it's penalizing you for trying to go outside.
I see. Okay.
Yeah.
And the second question is, you have that solution which has numbers.
Yeah.
Are the actual values of the numbers important, or only the relative ordering of numbers?
The values themselves are not important.
Only the ordering is.
Yes, but they have, this is the actual solution for a bunch of parameters underlying this, which I'm not putting there. There's a gamma parameter, which is the foresight. Okay, the last one I'll mention is not an example that we'll see in the coursework, but it's just to make the point that I don't need discrete number of states or discrete actions. So I can play with a continuous state system like balancing a stick. So here you imagine you want to balance a stick on a cartwheel. So this is called the card pole model. And then you want to balance the stick upright. And so what you can do is then you can put impulse at the base, right and left with a certain magnitude to keep the pole actually balanced. So we do this actually on the pole. If you're brooming your floor and then you want to play a bit, then you want to just stabilize your broom like this, and then you know that you have to move, right? And then we have kind of an instinct actually how this has to be done, but if nobody has played the game, then you try first and then whoop, it falls, right? So no reward there. Then you try again, and then there's a bit of movement. Oh, it worked, but then it falls again. And so you repeat, and then you get to the full dynamic. So how can I model this? So the state here will be the stick angle, like this. The actions will be either pushing the cart left or right with a certain impulse. The dynamics of the whole thing is basic physics 101. So you have to code this. And the reward in those cases will be that, oh, you'll get a 0 actually as a reward if you balance, but you get -1 otherwise. So this makes the point that instead of putting a positive reward for doing something good, what you can do is that you can give negative reward for doing something bad. It's the same thing. So it rejoins the question. The value of the reward itself is not so much important. It's how the rewards actually compare for the good actions versus the bad actions. Okay, so here I could put the reward 5 for being balanced and 0 for imbalance, but we can choose to have 0 for being balanced and -1 for being unbalanced. So you'll try to maximize your reward, so you'll try to reach 0 as much as possible. And so in this case, what's the optimal policy? We don't know. But we would have to actually code the theory and then code the equations for the system to learn with time how to balance this. And then you can do this in a simulation. You won't have the time to do this, but in the course I give in South Africa, this is also part of a coursework, balancing the card pole. So initially you start, you see the card pole is doing something stupid, not balancing, and then as you simulate and simulate and simulate this, restarting the system, then you see the system is able to learn to code, to control, and then with time, it's just moving, just jittering just a bit like we know it should do in order to keep the pole balanced.
For the machine to learn it, I mean, does it need to be told physics or?
No, this will be encoded in the dynamics, right? So I have this transition probability for if the system is in this state and I take this action, then the future state of the system will be this. Here it's a deterministic system. So the dynamics, the physical dynamics is encoded in the dynamics. So it's encoded in this.
No, but do you need to tell it like Newton's law?
Yeah, this is in the background.
It's there.
Yeah, this is part of the dynamics. So the model will always, it has a dynamics. The agent actually has to choose action. That's the policy. And then there's a reward structure. But the dynamics has to be specified. So you're interacting in a given world that has its own dynamics. The dynamics has to be given.
No, because I'm saying like when we do it, we don't need to know.
Oh, yes. Yeah, in control theory, in fact, yeah, but for the simulation, you would have to code the simulation. Yeah, exactly. No, yes.
Yeah, that's what I'm saying.
Yes. Okay, I get the question. Yeah, the question. No, the agent doesn't need to know physics. Yes, doesn't need to know Newton's law. It only needs to act according to maximizing a reward. In a sense, though, it's learning physics as it does so, right? It's learning gravity, right? Partially. It's not learning the laws of gravity, but it's learning some aspects of gravity. Okay.
So, a question from online, Hugo, sorry. So even in the previous example that you had shown, the numbers that you have put in the maze, like in the grid, right? So that exactly means that your system are so the numbers that you have put, your agent needs to explore everything possible in the universe, in this particular space. So wouldn't that be like too much of a computation to go for in order to choose the optimal policy?
So in the solution here, this is the solution, right? So this is what finally the agent has to learn. Of course, it doesn't have to learn. It's going to go like this now. And it's going to go. So it's not going to visit this part of the world where it doesn't have to go, but there's still a solution there. So if you decide to go there, it's telling you you're going in the wrong direction because it's giving you the value in the future. And it's telling you that you're decreasing your value in the future. So you're really going in the wrong direction. So these numbers have meaning. It tells, for instance, if you're here, this is -19. It says that it takes now 19 steps to reach the exit. whereas you started with a state that had 16 steps, so you really went in the wrong way. So as an agent, as you move, you should move to states that increases the reward. Here I have a negative reward. So from -16 to -15, here I have to get to -14 and then so on. So if I have the solution for the value function of the system, I know also the optimal policy. We'll get this again. The relationship between actually solving the problem with the value function or with an optimal policy being equivalent is something that we'll actually spend some time explaining. So maybe I'll leave also the question suspended here just a bit. I don't want everybody to understand what I mean by pi star and then v star here. These are the objects that we want to learn and learn from and define in the first place.
Is the uniqueness guaranteed for v star?
A task could have multiple optimal solutions. For the examples that we'll work on, actually, there's a single optimal policy. But you could imagine you could have also a degeneracy and the optimal policies that you have. So in as much as this is one possible solution, you can imagine actually all these other arrows defining other policies. So you have actually many optimal policies in this case. So the solution is not unique in that sense. Okay?
So, can you then not formulate any RL problem as a calculus of variation problem?
Yes. So that's a very good question. The question is it not related to the calculus of variation? It is. It's related to optimal control theory, right? So the way I phrase it now will be the language of Markov decision process, but especially the last example with the pole, you could phrase the problem as a control problem and as an optimal control problem. And for solving this continuous now optimal problem, optimal control problem, you would use the calculus of variation. So the idea is that you want to minimize some function. And so you want to choose the dynamical system that maximizes some function. So from that point of view, it's very much related to the calculus of variation. So what we're doing is a discrete time version of this, and moreover, it will be discrete space, okay, just to make the whole theory easier.
The example you showed is kind of about finding. So how does it compete with other part finding?
Well, we can discuss this, but if I want to solve the maze problem, it's a path-finding problem. But this example now of the card pole is not a path-finding problem. I wouldn't describe it this way, right? But it's a reinforcement learning task. So reinforcement learning, if you fix the reward structure, will give you the equations to get the optimal solution. It's not one method that is approaching something. It's the theory of how you should get what you should do in order to get the maximum reward in the future. Okay. Then there could be some approximate algorithms for certain tasks that can be compared to this, but this is not what we'll be discussing. Okay. Okay, so I think I'll stop here with the slides and I'll start with the first chapter on Markov processes, just as a recap to set the notations also. And so I'll finish chapter 1 today. And then we'll start Markov reward process on Tuesday, and then we'll finish chapter 2 already on Tuesday. And then we'll reach chapter 3 on Friday, which is the main chapter, Markov decision process. So this is chapter 1. And again, the lecture notes are on the GitHub. So if you don't get everything, then you can find the lecture notes there. It's really a scan of what I have myself here. So, so it's a recap again on a Markov process. So here a Markov process won't have any action. It's just a state evolving in time. But I want to see this just so that we get the notation for Markov process, what the Markov approximation is doing. And then we'll put the reward in chapter 2. And then in chapter 3, we'll put the agent as well. So here we're going to start with only one state. The state is S at time t. It's part of some state space, which I'm going to write like this. And t is the time. And it's going to be discrete time again. So time is 0, 1, 2, like this. So this is discrete time. Okay. So this is a random variable. So I could put here, this is what we call the state space. And the state itself is capital S. And now there's the Markov evolution. So what I want to specify is the probability that at time t plus 1, I reach a certain state S prime, given all the paths of the system. So at time t, I'm in the state S. At time t minus 1, I'm in the state something, t minus 2. So in principle, the whole dynamics, actually, the transition from going from S to S prime should depend on all the paths. What the Markov model does, or what the Markov approximation does, is to say, well, actually, the transition will depend only on the previous state in time. So, and this is a Markov evolution. This is an approximation in general for, this is plus 1. Okay, so this is the Markov property. If you have a stochastic process evolving in discrete time, in general, the evolution can be driven by the whole path. If you write a Markov model for it, what you're doing is that you're just assuming that the probability from going from a certain state in time to another state depends only on that state in time t. So everything is really given in terms of transition probabilities. You have probabilities for making a certain transition between a state S at time t to another state S prime at t plus 1. That's the Markov model, and that's what we'll be using ourselves as a model. Okay. So we say sometimes that the future is independent of the past, giving the present. So this is a property. The way that we're going to write this actually as the Markov chain is that we'll say, well, we start with a certain state at time 0, and that triggers a certain transition to a new state 1. That triggers a new transition, and then so on. And so you see that the transition to reach a state depends only on the previous state. That's kind of the diagrammatic way of expressing a Markov chain. So you want to stress that the evolution depends only on these arrows that depend on the previous state. And so everything will be determined by the probability of making a jump, probability of each of the jumps. And this probability we call the transition probability. So I'm going to write this in simple form as just P of S prime giving S. So that's a conditional probability. That's the first thing we have to observe, is that it's a conditional probability. Given that I sit in the state S, what's the probability now of making a jump to a new state S prime? So this will be my conditional probability. So this, if I write in full, is the probability for the random variable to reach S prime, given the previous random variable to be. Now we'll make many assumptions about this conditional probability. We'll assume that it doesn't depend on time. You see, I have time here, so the probability in principle can actually depend on the time at which you do the transition. But we're not going to do this. So we're going to assume that this depends only on the states that you want to reach. It doesn't depend on the time at which you do the transition. So this will say that this is time independent. And in the language of probability theory, this is what's called the homogeneous Markov chain. It's also called autonomous, stationary. And of course, we have the normalization. So these are probabilities. So we have that if I am on some state S and I look at the probability of doing a jump now to any state S prime, then I need to have this equal to 1 for all the state S, right? Everybody sees this. I'm sitting in a state S. I have a bunch of possibilities now for jumping to different states. These possibilities transitions are assigned different probabilities. If I sum all these probabilities, they have to sum to 1 because I have to jump. Okay, now if I look at this object, this looks like a matrix, right? It's an object that depends on 2 indices. So I can write it as a matrix 2. This is called the transition matrix. So I can write it in different ways. I'm going to write it with a capital P with the indices ij. And this really will be now the probability of reaching j, given that I'm in the state I. So if you look at the way that I'm ordering the indices, I'm going from I to j. So this is the probability of going from I to J. Okay, this is a matrix, right? You see this, it's a table of elements. They will sum to 1. So as a matrix, it's got size, the size of the state space times the size of the state space. It's a square matrix. The normalization here will come that if I sum over all the J's, it's equal to 1 for all I. So this is the same normalization that I have here. And as a transition matrix, all the elements between 0 and 1. Okay? So it's a matrix, but it's a special matrix. We call this a stochastic matrix. Or it's a Markov matrix. This
Hugo,
matrix I can
is it,
also diagram. Yes.
Hugo, is it symmetric actually?
No, it's not symmetric necessarily. And so I'll show this. So for instance, I'll give an example. Let's give an example, for instance. Suppose I have 3 states. I have 1, 2, 3. So I can put them actually as some kind of nodes. And I could have the probability from going from 1 to 2. So this will be my P1, 2. Now I could have also the other probability of going from 2 to 1. So this will be my P2, 1. But it doesn't have to be the same as P1, 2. So the matrix is not necessarily symmetric. Moreover, I could have a probability for staying in this state. So this will be my P1, 1. So the diagonal of the transition matrix actually gives me the probability of staying in a state. Okay, so I can do a transition, but I can include in making a transition to stay in a state. So these are self-loops. So you see that the Markov matrix actually, I can represent it in a diagrammatic way like this by putting all the arrows corresponding on all the possible transition, and the weights of the arrows will correspond to the probability. Okay, and that's something that's very useful. We're going to use this a lot. Actually, I showed this implicitly for the linear model for the robot model because I put the nodes and I put the arrows for the transitions I could do. Okay, so from this point of view, the normalization is that if I am in the state I, and I look at all the arrows going outside of I, the weight of all the arrows have to sum to 1. So if I do a sum here, it has to be equal to 1 because I need to jump somewhere, including actually jumping to the same state. Okay? Okay. This is a Markov model. If I specify the dynamics of Markov dynamics, what it means is that I'm specifying the entries of a transition matrix. I'm specifying the entries of this transition matrix. So I'm specifying all the probabilities of going from S to S prime. If I specify all these numbers, I write down a Markov model. So I have a certain number of states. I need to determine what the transition probabilities are between those states, and that gives me the Markov model. From this model, now I can calculate differently. And what we want to calculate is the probability distribution. The probability So from the dynamics, I want to be able to calculate the probability that I'm in a state S at time t. So I'm going to write it like this. This is the probability that if I run the dynamics from some initial condition, I reach the state S after a time t. Okay, so in this diagram, I can imagine actually starting in state 2, and I run the dynamics. So maybe I have a certain probability of staying in 2. I have a certain probability of going there. So I can determine which of the 2 events will happen, and then I do the event. Then I run the dynamics again, and then I'm going to moving on this graph. And so after time 10, for instance, I can say, what's the probability that after 10 time steps, I reach the state 3? So this is a valid question. This is actually has to do with prediction. We have a dynamics and we want to predict what's the behavior of the system in the future. So what I want to calculate is this probability. This is a probability vector. So before, I'm going to write down actually an equation for getting this distribution out of the conditional probability, okay? But the crux of that equation is to see that if this is a matrix, this is like a vector. So let's write it as a probability vector. This is time dependent. Of course, we'll be interested in making predictions in a long time limit. And so we want to reach maybe some stationary distribution in some time. But for now, I want to be able to really predict at a given time what's the probability of reaching a certain state. That's the ultimate object for prediction, right? Yes, so this is where I'm going now. So the probability vector, I'm just going to introduce some notation. I'm not going to put some vector. I'm just going to write it like this, right? The component of that vector, I could write it like this. This will be the component I. What's this? This, in my notation, will be something like, it's the ith component of PT. So I'm going to take this guy to be a vector. What's the size of that vector? Okay, so this is a S-dimensional vector, and moreover, it's normalized. Okay, I'm going to take this to be a row vector. And it's normalized, so if I take the sum over all the i's of PTI, this is equal to 1 because this is a probability distribution. Okay, it makes sense. I'm just using now a language of vectors and matrices because it makes sense. This is a 2 indices object. This is a 1 index object, so I have a matrix, and this guy is a vector. And this will be useful now. Yep. Oh, yes. So here you could say, I said stationary. I said also autonomous. We use this a lot in engineering. Autonomous. Homogeneous. Homogeneous is used in probability theory. For us, it will be like time invariant, time independent. Stationary means something else too. Yeah, yes. I'm aware of that. But if you use stationary in the context of the transition matrix, it might also mean that the whole thing is time independent. Okay, so I want to get to this equation before we finish. I think we have some time. That's good. And so the evolution equation is what we call the Kolmogorov equation. It's a matrix equation. And it says that at time t plus 1, if you want to reach the state S prime, what you do is that you have to sum of all the possible transitions that will lead you to S prime, starting at the time t from S, and then going to S prime from S. Okay, so this makes sense. This actually you can derive just by marginalization of random variables, but this is the Kolmogorov equation, the forward Kolmogorov equation. Kolmogorov. It makes sense from a diagrammatic point of view because if I look at some state S prime, there are many arrows that will lead me to S prime. So I have to look at a given S. So what's the probability of being in that state already and making transition in one time step, so from t to t plus 1. And this here will be the transition probability. But I have to do this for all the states actually mapping to that state. And so this is what the equation is telling. But this equation really is a matrix product, right? This is a vector, and this looks like this is a matrix. So it does look like a matrix product. And in fact, I can write it in matrix notation. It's a set of equations for all the S primes. Yes. So I'm going to write it as my vector t plus 1 is equal to the vector t times the transition matrix. So let's make this more explicit. I said that the probability vector was a row vector. This is also a row vector. And the transition matrix is a matrix. So I have a row vector that's going to give me the row vector. The fact that I don't have column vector is because the conventional use. Here I'm going from I to j. If you flip the convention, then you'll be multiplying column vectors. You might want to prefer this. In physics, we prefer column vectors. In probability theory, they prefer row vectors. Okay. So with this equation now, I can actually engage the dynamics and get the probability in time. So I can start with an initial state. That's the initial distribution I choose for my state. That's the initial distribution. Okay. Then what I do is that I want to, from this distribution, calculate the key at the first time step. So according to my equation, I only have to do this. One matrix product is going to give me the probability for all the different states at time one. And then I can repeat this. 2 will be now P1 being propagated, but of course P1 has already been propagated, so it's like propagating twice with the matrix, the initial state. So propagation of probabilities for a Markov chain is matrix multiplication. So I'm going to have now, again, T plus 1 is PT multiplied by pi, but it's also the first initial distribution that I put to the power, I have to do things now, T plus 1. Okay. So that's the Kolmogorov equation. That's not the only thing you can do with a Markov chain. With this, you have the prediction for the future. You can predict what the probabilities for the future over the states will be, but you can also use the Markov model to calculate expectations in the future. And this is very important for us because the goal of reinforcement learning will be to maximize expectations. We want to maximize the mean reward. We want to maximize the expected reward. So we need this notion of expectation. So I'm going to define expectations. The expectations we'll be looking at are, I'm going to write these expectations like this. It's a function of the state at time t plus 1, given that at time t, I start at some state. This is what we call a conditional expectation. This is the kind of expectation I want to calculate in reinforcement learning because I want to calculate really the future reward if I sit in a given state. So this will be the one-time reward, for instance, that I get by making one transition. Okay. Okay, so what's this distribution? You see that here I'm only doing an expectation. So this is the expectation sign. I'm not using the angular brackets that we use in physics. This is the expectation with respect to this random variable. So if I write this, what is this? This is, I evaluate the function over all the states I can reach, but I also have to wait with the probability of reaching those states. So this expectation is really a sum over also the transition matrix. Okay? Let me write it like this. I'm also going to have a matrix notation for this one. I'm going to write Fi, the expectation over the new state being transition, if I start in I. And here I could write actually that this is the sum over j of the function evaluated and the probability of reaching that state if I start at I, right? So I just rewrote this to here, but now I'm using I and j's instead of s and s product. But what do we see here? It looks also like a matrix product, but now it's a column. So I could write now my f as a column vector, and this will be my p as a square matrix, and this will be the function f as a vector. Okay, and so f here will be p times f. But now I see these guys as vectors. Maybe I should put actually bars or vectors. I don't know. I could put bars here, but I don't like doing this. So. Now, here's the P. Because this is actually now, yeah, no, that's good. Then you know this is Pij with the Fj on the other side. So it's like, okay, so I have two important results. And then these results actually will be used all along when we use the Markov decision process. If you want to propagate probabilities forward in time, it's a row matrix product. If you want to calculate conditional expectation, it's a column matrix product. Okay, so you take the function you want to take the expectation of. This is a vector, right? I'm just saying that this is the vector with these components. Then you multiply the matrix on this side, and then you get all the conditional expectations for all the different states. Okay? The fact that you have row vectors and column vectors is actually related to a notion of adjoint for matrices. Okay? There's an inner product here underlying this. I don't want to talk about this, but it's built in here. Okay.
I have a question, Hugo. Who gives me the law for the transition probability from I to J? I ask this because this looks so familiar to, the formalism of quantum mechanics, right?
Yes, of course. In a sense, this is a classical version of quantum mechanics. Instead of talking about transition amplitudes, where we have transition probability. So everything is classical. There's no interference possible. I just have to fill in the entries of the transition matrix P. So the transition matrix P is also called the propagator.
Right. But in quantum mechanics,
it propagates the probabilities. So this equation here for the evolution equation is a discrete version of the Schrödinger equation in a sense, right? For the Schrödinger equation, we would have a differential equation for the evolution of probabilities, which in the theory of Markov processes is called the Fokker-Planck equation.
Right. But I am asking you, what gives the law? In quantum mechanics, I know what the law of nature is.
Yes.
What's the law here?
Yeah, in quantum mechanics, the evolution is determined by the Hamiltonian.
Right.
In a sense, if you not just in a sense, if you specify the Hamiltonian, you specify completely the evolution.
Right.
Here, implicitly, the evolution for us is contained in the entries of that matrix P. We don't have an Hamiltonian as such. There's no notion of Hamiltonian. We have a dynamics that's entirely described by the various probabilities of making transitions. What's non-trivial about this is that you have this linear algebra structure. So in order to find, for instance, the probability at the second time step, it's very easy. You just multiply the initial distribution with P twice. So this gives you the full propagation of the probabilities. So in a sense, P square actually will contain all the transitions that are being done in 2 steps. P3 will give you the transition probabilities for making transitions in 3 steps, and so on. And so this is how the dynamics is being evolved. So it's less explicit than in physics, where we have the Hamiltonian, and the Hamiltonian is the generator of the propagator. Here we don't have a notion of generator. Okay. I'll finish with 2 simple concepts that we need.
Hi, this is Agnes again. So a quick question, where is the notion of reward? So this is related to Spencer's question. Given Hamiltonian is driving the dynamics, there should be some notion of reward here as well.
Again, I didn't understand the question.
So where is the notion of the reward?
Oh, no, there's no reward at this point. Reward will come in chapter 2, so on Tuesday. So I just want to introduce the basic model, this notion of Markov process, this notion of Markov chain. So we're going to have a random dynamics that's given by a Markov chain. So I haven't put any reward at this point. And I'll
So
there's no age.
I see. My understanding is the Hamiltonian dynamics will be equivalent to the notion of reward here.
Oh, this I don't know. We're not going to see. We're not going to see the notion of Hamiltonian. We're not going to see any physics to some extent, right? So the dynamics is given as it is as a Markov chain, and then we're going to study this. We're going to put an additional random variable, which will be the reward, and then eventually we'll put another random variable, which will be the agent. But I'm not going to define the evolution in any physical way. So no Hamiltonian, no quantum dynamics, just Markov chains, okay?
And these probabilities are not related to the reward.
No, not at this point. This is coming for Friday next week.
Okay.
So given the properties that we have for P, if we know P at some time T, can we go to the initial one?
Yes. Not quite. No, it's a many-to-one mapping, so it's very non-trivial. Yeah, because in fact, many different initial conditions can lead you to the same PT. Right, and then this is going to be clear when we talk about stationary distribution. Okay, so I just want to finish with two simple concepts of probabilities that I would assume you know, but I just want to put them out because we're going to use them a lot. The first one is the notion of marginalization, which is about, suppose I have a joint probability distributions for two random variables, P of X and Y. Out of this, I can get the distribution just of X. And the way to do this is that I marginalize over Y. I sum over all the possible values for Y. This is called I marginalize Y, or I trace out Y. The trace out is the word that we would use in physics. I could use the same for Y by summing over all the X. So I could trace out X. Maybe I want to be a little more precise. If I have a joint distribution, this will be the distribution of the random variable Y. This will be the distribution of the random variable X. Okay, so this is marginalization. There's something else basic, which is called the chain rule, which is I can always write a joint distribution as the marginal distribution times the conditional distribution of Y given X. All right, so these are called marginal distribution. If I have a joint and are marginalized, I get a marginal distribution. A joint can always be written like this, and this is basically Bayes' theorem. P of X times P of Y given X. Or I also have the choice of writing this as P of Y times P of X given Y. And if I equal the two, then I get Bayes' formula. Okay, so I'm going to be using this a lot, actually. We're going to marginalize over the agent. We're going to marginalize over the reward. So we need to remember these rules. And this one is the chain rule for conditional probability. There's something else that I'm going to be using a lot is that in some cases, we're not dealing with noise, we're dealing with a mapping that's given. So it's a kind of deterministic relationship between X and Y. And I'll finish with this. If you have deterministic transitions, what it means is that if I start with a given S, then I reach a given S prime with probability 1, which is a function of S, right? This will be deterministic transition. In general, actually, we'll take these transitions to be random. So we have certain probabilities from going from a state S to a state S prime. But in some cases, what we'll see is that from a given state S, you're moving with probability 1 to another S prime, which is given as a function of S. How do we represent this? Well, this is just a degenerate transition matrix. This will be 1 for the S prime corresponding to f of X, and it will be 0 otherwise. So this is something I mentioned at the start. Deterministic dynamics is a subcase of random dynamics. It's just a case where the transition probabilities are being assigned ones and zeros. Okay? So this will be important for the agent. The agent, at some point, the policy will be in this form, and the agent will take a specific action in a specific state. So the agent will be deterministic. This is actually a major result in reinforcement learning. An optimal agent is always deterministic. There's no value in doing randomized action. Okay, and then we will get this. This is far down the line. Okay. Okay, so this closes chapter 1. I had in mind to start chapter 2, but I think we've seen enough today. So I'm going to leave. We're going to do chapter 2 on Tuesday. So again, I should probably say next week is not Monday. The lectures will be on Mondays normally, but next week we're going to have Tuesday at 3:30. Exceptionally just for next week. And then we'll revert back to Mondays at 2 o'clock. Okay? Any questions? In the class, online?
I have a question. Yeah.
Yes.
So, I mean, we know, I mean, one knows that if you have this Kolmogorov-Fokker-Planck type of equation, then in a sense is equivalent to a stochastic process, actually.
It is a stochastic.
Right? So I guess that's maybe something you may want to say. I mean, there's deterministic, but also there can be a stochastic process. What I wanted to know is, I mean, how is the noise correlator sort of determined, or?
We would have to determine the noise if the underlying model was some kind of stochastic differential equation.
Yes.
With Brownian noise or
Right.
Here, it's a simplified model. It's a different type of Markov process where I have discrete state and discrete time, and so there's no notion of noise itself. The transitions are noisy, but only in the sense that I'm assigning different probabilities to different transitions. So I'm treating the transitions as random transitions. But there's no noise explicitly like you would put in a stochastic differential equation, like in a Langevin equation, for instance. But we could actually do reinforcement learning on Langevin equations. This is possible. You can take, as an underlying model, a Langevin equation in continuous space, continuous time, with an agent that's trying to control that equation. But we're not going to do this. To keep the theory simpler, we're going to deal with discrete state and discrete time, and this is the model of a Markov chain that has no explicit noise.
Thanks.
Anupam?
I want to get some clarification. So you said that in the reinforcement learning, reaching the goal means that you want to get a solution, deterministic transitions. Is it that?
We'll see. We'll see when we get there. Just to anticipate, I want to find the best way to choose my actions, and this way of choosing action will be deterministic to control a stochastic system.
Yes.
What's funny is that the best way to control a stochastic system is with a deterministic agent.
So it's an answer to this question that what is the best way to perform the task?
Yes.
To reach the goal.
Yeah.
But will you also describe how the learning process which the Markov process changes these rates?
Yes.
So then if it changes the weights with time, maybe they are not explicitly time dependent. They're still at each step.
Oh no, it will be time dependent. We'll see this. Yes.
Today you said that it's
No. Just for the purpose of the chapter 1, keep things simple. Yes.
Okay.
Yes.
Thank you.
So just a question about this P matrix. So it seems like so the left eigenvectors of this matrix usually are related to the stationary distribution, right? What about the right eigenvectors here? They seem like they'll be related to the.
There are many actually. So this is a good question. So this is an important question if I was teaching Markov processes, but not so much for machine learning actually. So the question is about P is a matrix. So there's a certain stationary distribution which does not evolve in time. So in some cases, depending on the model that you write down, you can have that a special vector that's like this. This is the stationary distribution. You use this distribution as the initial state, you evolve it, you get the same distribution. So P star is a stationary distribution. In some cases, you have one. In some cases, you don't have any stationary distribution. In some cases, you have many. If you have only one, it's an ergodic Markov chain. From the point of view of linear algebra, it's a left eigenvector of eigenvalue 1. And so the question is, can we imagine the same on the other side? On the other side, related to the eigenvalue 1 is the 1 vector. The 1 vector is the normalization of the probability. So if I do my P like this, and I just contract with a bunch of 1s, then I'm going to get a bunch of 1s. And this is just coming from the normalization. So the 1 vector is an eigenvector. It's a right eigenvector of P with eigenvalue. But there can be other ones on the other side with different eigenvalues. The spectrum of P is very important in the theory of Markov processes. We're not going to discuss that. I'm here actually to write a book about this. This is the book I'm writing. Yeah. Other questions?
Can you say the right eigenvectors measure that expectation equation?
Yeah, there's lots of spectral properties actually about P. Interesting space. So this is just, so the P is not symmetric. This is why it has different left and right eigenvector. If it were symmetric, then they would be the same, and not here. So so there's lots of eigenvectors left, eigenvectors right. They have the same eigenvalues, of course. So the spectral properties of P is something, it's a topic on its own. It's very interesting. But for reinforcement learning, we don't need that. We just need the idea of what a Markov chain is. That's it. Because that's the basic model we use. We'll just tweak it to include an agent and include a reward. Okay? Okay.
So P need not be diagonalizable also.
Oh, no, no.
So if it is, then we know, right? If we know P to the power something, then we can calculate P also.
Yes, but the P to a power still makes sense, even if it's not diagonalizable.
It does.
And P will always have this eigenvector by normalization.
Yeah.
So it has eigenvalue 1 for sure, always. All the other eigenvalues actually will be below 1. So this is the maximum eigenvalue. Same thing here.
Oh,
So
this one is corresponding to this eigenvector is corresponding to this.
This is the dual of the 1.
This one, yeah.
Okay. So there's lots of property. It's not the same as in quantum mechanics because we don't have emission. Okay. I think it's a good time to stop here and breathe a bit, and then we'll start again on Tuesday with Markov reward process. So the goal next week on Tuesday is just to add the reward, not the agent yet. Then we'll put the agent on Friday. Good. Thank you.